Hello and welcome. In this video, we're going to look at three examples of probability that are going to be on the edge of what I would expect students in this class to be able to complete. If you're able to follow along and complete them, that's fantastic. If this is a little bit on the challenging side for you, don't worry about it. These topics will not be on any test or quiz, but they're kind of, like I said, much more advanced applications of probability, which will help us to hopefully understand future applications of statistics when we get into modules 5, 6, 7, and beyond. So it says that 3 good batteries are mistakenly mixed with 2 defective batteries, which all look the same. If you know anything about batteries, batteries that are fully charged and batteries that do not have any charge left look identical. So imagine that you have a junk drawer. Some of us have junk drawers in our kitchen. So I'm going to draw here. We have a drawer here, little handle. We have to pull it, open it. It says that 3 good batteries are mistakenly mixed with 3 defective batteries. So I'm going to simplify this. I'm going to write bad. So we've got 3 good, 2 bad. If we were to randomly choose 2 batteries without replacement, we'll talk about that in a second. What is the probability? And then we have a bunch of different probabilities here. Well, if we wanted to label this, we could. We have 3 good batteries and 2 bad batteries in our junk drawer. We would reach into this drawer and we would grab 2 batteries without replacements. So that means that we would grab 1 battery and then we'd reach in and grab a second battery, meaning that the probability of choosing the first battery would be either 3 or 2 out of 5, and then the second battery would have a second probability that would be out of 4, depending on whatever the outcome of the first selection would be. So we're going to use the multiplication and addition rule here because the sample space would have a total of 20 different outcomes. Oops, sorry. Right, so the first selection would have 5 potential outcomes. The second selection would have 4 potential outcomes. So using the fundamental counting principle, we have a total of 20 outcomes. I think we could do this a little bit faster by just using the probability. So the probability that exactly 1 is defective. Again, defective just means bad. So what does that mean? Well, that means that we have a good on the first and a bad on the second, or that means that we have the probability of, oops, put the parentheses in the wrong spot, the probability of a bad on the first and a good on the second. Good on the second. That's how we can get only 1 bad battery. So the probability of good on the first would be 1 out of 5. Sorry, not 1 out of 5. I apologize. Let me go back and double check this. So we have 3 good batteries. We have a probability of 3 out of 5 on the first selection times, well, if I were to remove one of these good batteries, then I would have 2 bad batteries out of a possible 4 that I could choose for the second. I could also have, though, see if I can erase. Oh, I erased part of the, oh no, I erased a bunch of the lettering. All right, for the second possibility here, a bad on the first and a good on the second, well, we have 2 bads on the first out of 5. And if I select one of those, then I'm left with a 3 out of 4 probability on the second, because I have 3 goods that I could select for the second. So multiplying these and adding them, this would be 6 out of 20 plus 6 out of 20 would be a total of 12 out of 20, or the same thing as 3 out of 5, if we were to simplify it. You could also use a calculator, find it be 0.6, or 60% if you wanted to convert this to percent. The next example here says that both batteries are defective. Again, defective is another way of saying bad. So how would we get both batteries bad? Well, bad on the first and bad on the second. There's no other way of getting two bad batteries. It has to be this. So a little bit easier, using the same visualization that we have from the previous example. There are two bads for the first selection out of a total of 5. And if I remove one of those bads, then I have only one bad for the second selection out of 4 left over. Again, that's what it means to be without replacement. So multiply this, we would get 2 out of 20 or 1 out of 10. Again, if you wanted to, you could type this into your calculator and you would get 0.1, which would be the same thing as 10%. For part C, both batteries are good, so the probability of a good on the first and a good on the second. There's only one way of getting that, be good on the first, good on the second. There's no other ways we could work with this one, as we did in part A. So the probability of getting a good on the first, well, we have 3 good batteries for the first selection probability out of 5. And if we take one of those good batteries away, we're left with only 2 for the second selection out of a total of 4. So this would be 6 out of 20, which would be, if we reduce that, divide top and bottom by 2, it would be 3 out of 10. If you type this into your calculator, it would be 0.3 or 30%. And then lastly, at most 1. At most 1 means the most that it could be is 1, so it has to be 1 or less. 1 or less. Battery is non-defective. Well, we were crossing off the word defective and writing bad before. So if it's not bad, that means that it's also good. So 1 or less good batteries. So we want to have the probability that we get 1 good or the probability that we get 0 good batteries. Well, this is going to be a little bit complicated. The probability of getting 1 good battery would be the probability of getting a bad battery on the first and a good battery on the second, or the probability of getting a good battery on the first and a bad battery on the second. So that's the expanded form of these, the only 2 options we could have for that. Or we could have the probability of getting a bad and a bad. So the probability of 0 good would be that we get bad on the first and bad on the second. That would give us no good batteries. And luckily for us, we've already done these calculations. The probability of a bad on the first and a good on the second, we did up here. And the probability of a good on the first and a bad on the second, we did up here. I accidentally switched the orders from part A, but it's the same thing. So in part A, we know that we had 12 out of 20. And we've already done the bad out of bad and bad, which is actually part B. We've already done that one as well, which is 2 out of 20. And we can add all these together. We would get 14 out of 20, which would be the same thing as, if we divide it by 2, 7 out of 10, or 0.7 in our calculator, which would be the same thing as 70%. So that's how we can use the multiplication and addition rule for probabilities. I went through this rather quick. If I went too fast, feel free to rewind, pause, work on this alongside of me as well while you're working through this question. We're going to move on to the second example of this video, which says approximately 9% of men have a red-green color blindness, which prevents them from distinguishing between red and green. If 3 men are randomly selected from the population, what is the probability that all 3 of them will have this red-green color blindness? Well, in order for us to figure out this probability, we would need to know what the outcomes would be. So I'm going to use the words or the letter CB for them actually having the color blindness. And the outcome of this experiment would be to select 3 people from the population and knowing whether or not they have the red-green color blindness. And we want to know what's the probability that all 3 of them will have it. Well, that would mean that the first person would have the color blindness trait, and the second person would have the color blindness trait, CB, and the third person that we select has the same color blindness trait. And there's no other way of doing this. If there was maybe 2 of the 3, we'd have some or statements in there because it'd be the first and the second would have it, but the third wouldn't have it, or the first and the third have it, but the second doesn't have it. So there's no ors in here. We're just going to do the ands, and we know that any person in the population will have a 9% chance of having the color blindness. So we're just going to have the 9% probability being applied 3 times, because this is the probability that the first person has it, this is the probability that the second person has it, and this is the probability that the third person has it. So all we're going to do here is to 0.09 times 0.09 times 0.09. Again, this is the first person, this is the second person, this is the third person, their probabilities. And then we would just type this into our calculator, and I'm going to just pause my screen for a second to confirm my calculation. .09 times 0.09 times 0.09 is 0.000729, and then we can round that to whatever place we need to round it to. And I have one more example here that is dealing with an example from the e-text that's going to look into the with replacement versus without replacement. So with replacement means that the first outcome does not affect the second outcome. And without replacement means that the first outcome does affect the second. And we'll look at these 4 examples. It says that there are 14 freshmen and 17 sophomore students in a classroom, and we randomly select 2 students. If the first student was a freshman, what is the probability that the second student is also a freshman? Well, if we have this room here, we have 14 Fs, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 17 S's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We have a total of 31 students. If we select the first person, and they're a freshman, but then we put them back into the population for the second selection, our probability will still be the same, 14 out of 31, because there are still 14 students that are freshmen in the classroom out of a total of 31. If the first student was a sophomore, what is the probability that the second student is a freshman? Again, we choose the first person, they're a sophomore, but then we put them back in the classroom. We replace them in the sample space or in the population. We would still have the same probability, 17 out of 31, because there are still 17 sophomore in the class of 31. Now, without replacement is where it gets a little bit trickier. Without replacement means that we remove them and then keep them out. And keep them out during the second selection. So that's what we mean by without replacing them. So if the first student was a freshman, what is the probability that the second student is also a freshman? Well, if we look back at our classroom that I drew for part A, if we take out one random F for the first selection, That means that we now have only 13 freshmen out of a total of 30 students left. Because we took out the first student, we removed them from the population, and we kept them out during the second selection. So it changes our total, and it changes how many freshmen there are in the room. And then for part D, it says if the first student was a sophomore, what is the probability that the second student was a freshman? Similar idea here. We choose any random sophomore from the class. But I'm going to put this freshman student back in, if I can. Well, if we took out a sophomore, that would mean that there is still 14 freshmen in the class, but now the class, again, only has 30 students for the second selection. So hopefully this video helps to explain the multiplication rule and the addition rule for and or connectors, and also the with and without replacement. Thanks for watching.